Yeah, it's been recording. Okay, first, this is not intended to cover the entire network security. Okay, so why don't we try to cover the fundamentals? I think the main thing people are interested in, the blockchain, and then the blockchain applications, for example, the Bitcoins, NFT. So those are latest applications, really associated or being based on network securities. So that's why I want to cover the network security before we can really move on to the next topic. So that's the reason. So I'm going to cover just enough for you to understand why we need the securities and what kind of applications can be based on the network securities. Okay, so that's the goal. Make sure this goal is being clear to everyone. So the first thing, okay, the securities, right? So we're talking about internet securities. So the fundamentals, I want you to be aware. Network, internet, especially I'm talking about internet. Internet has no securities. Okay, the reason internet has no securities because we are sending our traffic through the public network. So that's a very critical. The knowledge, very fundamental. Anything you send it to the internet, you have to assume, okay, there's no security at all. The internet is open, open to everyone. So openly accessible network. The reason the internet being so successful is because internet is being shared by everyone. So that's why it has a high efficiency, high utilization rate. So compared to, I think, 20 years ago, we always consider the two types of networks. One is called internet. The other one is called telephone network. Okay, the telephone network is considered not shared. Okay, so when I say not shared, because whenever you make a phone call, you dial a number, then you make a connections. Then this, once you have the connection being set up, then you use this dedicated line. Okay, I know that you still can tap into the phone line to hear what you can say, but then that's a different story. But nobody can actually use, at least use that bandwidth. We call it bandwidth is the communication speed, or the network capabilities is being allocated, dedicated to you. So that's what I consider, at least it's not shared. The internet is different. Internet, you don't really, nobody allocated the bandwidth to you for any connections. You only send packets. So it's called data network. You send it the packet. So whenever there's a bandwidth, you use that bandwidth. So everyone's sharing the network. So that's why it has a high utilization rate. That's the main reason the internet actually is become cheaper than your telephone network. Now, all of the phone network is really being replaced by internet because the cost issue. Internet is cheaper. Okay, that's one thing. Like internet is shared, so that's why there's no protections. You don't really have any dedicated bandwidth. Now, all the hackers can see your traffic, okay, because this is a publicly accessible. Everything's open to the public. So the basic assumptions, you send any message through the internet is considered it can be compromised. So when we say the compromise means that we can see it. There are plenty of devices that are watching the internet traffic constantly. Okay, so that's doesn't matter. You say, okay, this is unlikely people can just capture your traffic at the right moment. So what really happens is basically they can capture traffic and do the analysis later. So whatever you send to the internet is not secured. So how to make the network security? So that's what the whole network security is talking about. We're not going to talk about the whole thing. So for example, the peripheral securities, we're talking about the firewall. Okay, and then you also can have device to protect DOS attacking. DOS attacking means denial of services. Okay, you keep sending this junk service. The traffic to any server potentially you can utilize all the bandwidth, and then you can block the other people from accessing that services. It's called DOS attacking. So we're not talking about that. Firewall, there's different things. They just basically to block the traffic, not the legitimate traffic to your services. So there's a firewall. And there's a host of securities. For example, phishing. Phishing is one of the major attacking for the host. So basically you receive an email, and the app asks you to open that link. And you most likely very suspicious link. If you open it up, then you likely can download the backdoor malware or save something which could be harmful to a computer. So that's called host security. And then you have to really scan that any message. But basically, don't open any suspicious link. There's two types of things that can happen. One is a virus, and that one's a malware. Virus more happen in the early stage. So they just try to do something harmful to a computer. Malware not necessarily doing anything harmful to a computer, but then try to steal something or open a backdoor so they can come in later on to your computer. So there's a virus and a malware. So that's not what we're talking about today. Okay. Then we are mainly talking about here, communication protections. So when I say the communication protections, because I mentioned earlier, whenever you send traffic to internet, we consider is not secure. But now, how do we make them secure? This is called communication protections. Three things. Basically, if you go home today, I want you memorize, take home today for the communication securities. Three things you need to worry about. The first thing is called confidentialities. Confidentiality means you send the traffic to the public network, but then you send the network, you send a message with encryptions. So basically, you encrypt your message so nobody can see what you can see the message, but do not understand what it is. It's confidentialities. First thing, okay. Second thing important is called authentications. So basically, authentication means you know who sent the message to you. You know, you can send a message to anyone without the authentication means you can pretend to be anyone else. But with authentications, then you will be able to know the identity of the sender. So this is called authentications. The third thing is called integrity. So integrity means the person who sent you a message, or we just want to make sure the message never been changed, altered, or being add any additional information to it. So that's called integrities. They send it, this is the original message. So that's the three things you will take home today is these three things: confidentialities, authentications, integrities. This is to protect your communication, even though I said, okay, in a public network is not secure, but our computer technology can make sure the three things can happen. With these three things, then we still can ensure your message being delivered securely. So that's just three things here. Okay, hope that's clear. Here's the illustrations. Okay, so now this is a person. Okay, they send a message to the other person. What they do? So first thing is called encryption. So they have to encrypt, and then then in the receiving end, this person has to read this message. It's called decryptions. So encrypt and decrypt, and then you send to the other end. So assuming there's an intruder, this is intruder. So the intruder, what they can see, they still can see your message, but this is called a ciphertext. So with this ciphertext, they will not be able to understand what's in there. So this is called the, this is just a passive intruder. They just watching the traffic. There's an active intruder. They can alter your message, but with our integrity, we'll be able to detect is anything being changed. So this is an active intruder. Okay, now you can see to make this communication secure, we need to do a few things, right? First thing is encryption. Make sure the message will not be altered. Actually, we will not be understood by the intruder. And then we have to have the integrity checking so nobody can change the message. Now, what about authentications? Okay, authentication, we have not talked about this here, but authentication is very important, okay? But we haven't talked about here. Authentication basically means we have to confirm the identity of the sender or the receiver. So basically, A and B are talking, they have to sure who they're talking to. So if someone pretend, okay, if they're talking to A, but then there's actually a C being talking to B, and say, okay, I'm an A. So then you send everything to the A, actually being sent to C. So that's called, in this case, the authentication failed. Okay, so this is, they don't know the identity because it goes through the internet. And this happens all the time. So then we need to have at least 3 things, okay? Confidentialities, authentication, integrities. So that's what we keep in mind, the 3 things that can help us. Let's see, someone's chatting here. For now, VPN communication protection. Yeah, VPN communications can do all of the things. Now, encryptions. I give you a very simple example about encryptions. So hopefully you understand what it means. Encryption basically just you hide the message. Now, how do you hide the message? I give you a very simple message. Just take it from here. Okay, first thing, all the encryption algorithms are open. So in other words, hacker knows your algorithms, right? The only thing the hacker does not know is your key. The key is something hidden. The hacker doesn't know. So here, let me give you an example. Here's my message, right? The message, this is a binary message. The message can represent anything with this binary. So this is my message. Okay, here's the key. Okay, now here's the encryption. This is a very simple algorithm. How do we do the encryption? We do the XOR. XOR means whenever it's a 2, if you do the operations, if there's 2 digits are saying it's 0, if the difference is 1. So 1, 1 is saying 0. 0, 1 is different, 1. 0, 0 is 0. 1, 0 is 1. 0, 1 is 1. 0, 1 is 1. So this will be your encrypted message. How can you do the decryptions? Same thing. Okay, you have to know the key. If you know the key, you can do the XOR again, and then the message will come back. So you can see the 0, 1, okay, 1, 1, 1, 0, 0, 0, 0, 0, 1, 1, 0 is 1, 1, 1, 0, 1, 1, 0. So this message will be the same, identical as this message. So that means this will be what the hacker seen. This is what the receiver decrypt. So you can see they got the original message back. So now you can see this is quite efficient, but this algorithm is not complicated. Okay, this is a very simple algorithms. What I try to show here, okay, when you use decryptions, the most important is the key. Okay, the key has to mix with your original message. And then in the receiving end, you use the same key. This is called a symmetric encryption decryptions, symmetric algorithms. This algorithm is simple. The real algorithms are more complicated than that. Then you can use that to decrypt this cipher message and get a message back. Okay, now keep the word here, symmetric. So this makes sense. Okay, I think it's intuitive, makes sense. You use the same key to do the decryptions. So when you do the encryptions, mathematically, you can put it this way. Basically, you have a message, right? You have a message. You really want to use a math way to describe these encryptions. your encrypted message basically equals a function, okay, any function f, which use a key, and then with this original message, this is called encryption. What are we going to do with decryption? Decryption means you got your message back, but then you are doing with, we call the reverse function. The functions can be reversible. This is a reverse function. We use this notation. Okay, this is basically the reverse function is -1. Okay, this is not the right way. That's just my notation. Okay, not necessarily the standard. Standard notation is like putting the shoulder -1. Then use the same key, and then with the encrypted message, you get your message back. Okay, so that's I'm gonna make this is meaningful. I don't use message because I use M. I got a message M back. So that's basically encryption decryption. You can use any function f, which is reversible, and then you can encrypt and decrypt. Now the only thing you have to make sure, okay, you know the key. If you don't know the key, you will not be able to decrypt. So that tells you one thing: how secure your encryption depends on two things. One is your function f. Okay. Second is the length of key. Assuming you have a function which is secure, that means nobody can hack and do any analysis about your function. The only thing the hack can do is depends on your key length. Okay, understand the key length. If your key is a 1 bit, and a hacker, so I know if the key is a 1 bit, you only have 2 options, 0 and 1. I can try it twice and I got your message. I can guess. Okay, so the key length determines, assuming I have a function f is secure enough, the key length determines how secure the whole encryption will be. So any function f can be with reversible, can be used for decryption and encryption. When I say the reversible, I can give you an example, right? So if my f, okay, this is not necessarily the f I use XOR is reversible. Any function f, I give you an example, right? If I have a function called a +1, okay, this is an encryption function. So what's my reverse function for +1? Or I just use a capital F for the real function. What's my reverse function minus +1? Right? It's just everything you add 1 is encryption. I mean, your -1 is decryption. Get the things back. So anything is reversible. Okay, any math function is reversible. It can be used for encryption decryptions. It can be a math function or it can be anything. Maybe it's not a math function, anything you like to do. So this is called the function. So that's why when the function, the algorithm designer, they have to try in different ways to give your function complicated enough so people will not be able to eventually, when you go to the keys, the key will be evenly distributed. Okay, evenly distributed means you try to hide the key inside the message. So that's the goal for the define this function is just make the function a little bit more complicated. So then the people cannot just guess what the key is. The only thing they can do is use a brute force. When I say brute force means with all the combination of keys and try it out and see what happens. Okay, is this clear to everyone?
So is it so for a more complex key, you'd have something like a 10-digit or 15-digit key that is going to take longer using brute force to crack the key?
Yeah, I will go to the calculations. Okay, so you will see that. Okay, now let me come here. Okay, let's answer this. Actually, this slide answers 6 questions. So our encryption goal is make sure it takes more than a lifetime to hack the encrypted message with brutal force attack. All right, so that's what our goal. If you take more than your lifetime to do that, then we think it's a secure. right? After 100 years, who cares? No, this is not secret anymore. So how long the key will be secure enough? So in the past, we say 128-bit key. So how many combinations with the 128-bit key? Normally, if you have a 10-bit, is 3 zeros. So 128-bit, you have a 38 zeros in decimal, okay? So we consider if you try 38 zero times to be able to find out which key to be used, how long it takes to try that out with the fastest computer nowadays. Okay, roughly, it takes about a few hundred years. So that's why it takes more than a lifetime to be able to do that. Okay, that's the estimate. I think 20 years ago, they said 128-bit key is secure enough. Nowadays, as the computer speed really improves, and then recommendations are 256-bit. Okay, 256-bit. You can figure out how many zeros are for 256-bit. How many combinations you have to try with 256-bit keys. Now the people arguing, okay, nowadays we use CPU, GPU, maybe the quantum computing, they can increase speed 1,000 times. So by that time, maybe even for 256-bit may not be sufficient, then just increase the number of bits. So in general, if you use any security keys, current recommendation is 256-bit. So if you really want to try, if I have a very good algorithm, there's no way you can do the analysis and figure out, like a shortcut, figure out what the key is. That's, you really have to try every single combinations. That can take you 1,000 years, okay, with a 256-bit, the few thousand years. So then we consider this algorithm is secure. Okay, that's basically our encryption goal. There's no such thing as 100% secure. You know, the brute force, you can always try brute force. You can just try longer enough and you find the key. So that's that's something you cannot prevent. You know, the hackers can do a lot of things. So now it will take more than enough time, then we think it's secure. This is called the that's what we call the goal. So how are you going to make sure the hackers does not need to do they cannot do the analysis? It's called the analytical or analysis attack. Okay, and when you do the analysis, you can figure out, okay, without going all through the combinations, then you get the key out. Then this is not a good algorithm. Now, how are you going to avoid that? The best way, you can mix the key into the message. You really have to randomly mix the key into, okay, we say evenly mixed means there's a possibility with this key goes to 128-bit or 256-bit. In each bit, the key has the same probability of change. So in other words, you just don't know what change will be. So they're all equally likely. And you have to go through all the possibilities. So in that case, we have an algorithm which is good enough. And then we consider this algorithm secure. Okay, I give you some sense. One of the algorithms I like is called AES, Advanced Encryption Standard. So how this thing is doing, okay? Let me give you, do I have a, okay, this is the AES. So this is the AES. Basically, we don't have to go through all of the details, right? So the algorithm itself, so this is 1, 2, 3, 4. This is 4 bytes. 4 bytes times 4 bytes is 16 bits. 16 bytes. 16 bytes times A is 128. So that's how many bits you put in the array. So first you go through those are the algorithms to convert so many, it's a 128 bits to another 128 bits. They go through those things. Okay, this is encryption, this is decryptions. So first, they add round key. Okay, the round key is generated by the key, but this is not a final key. This is not the original key. Okay, so first you call the sub bytes. You do the subscriptions. Okay, do some subscriptions. Then you shift the rows. Then you use a mixed columns. Mixed column means times a matrix, and add round keys. And then sub bytes, shift rows, add round keys. Now, pay attention to, okay, it's not like one-time deal. They have to do a lot of things. They do this 16 times. So each time they do this, for example, the substitution bytes means this is a 1 byte. You substitute this byte with another byte. You have to make sure this is reversible. So you have to keep a table. Whenever you substitute this byte, then you know how to substitute them back. So this is called reversible. Same thing, you shift the rows. It doesn't matter how you shift the rows. Then you have to shift them back. So this is reversible. Mixed column, same thing. This is a times matrix. And then you times inverse of the matrix, you get this back. So this is reversible. Then you add round keys. Again, the round keys you're doing the X row, the XOR. So it's reversible. You do this 16 times. And then when you do the decryptions, you just do exactly the same thing. Everything's inversed. Then you can get them the plain text back. So that's what I said earlier. Any operations you do here, as long as you can have a reverse operations, you can apply them to encryptions. Now, we are not just apply a function which is reversible. We also have to find a function which is also efficient. So the AES algorithm is not just reversible, it's pretty efficient. So this is one of the best algorithm I like. Very, very efficient. All the operations here is very efficient. So that's back to here, right? So the encryptions now, basically, the encryption now is try to mix these keys evenly. Okay, not just like with any rules or patterns. You really have to mix them randomly. That's what I'm showing here. You do this 16 times. So in the end, you just don't know what happened to each keys. It's no way you can guess. So that's what the intention. You really want to see how this intuitive. Okay, assuming my message is a 4-bit. So all the possibility for this 4-bit message is a 16 combinations, 4-bit. The all possibilities is 16. So if you do this encryptions, what I want is any single combination of bit as a possibility to be converted to other combinations. And this conversion is randomly being, computer science has never been truly random, but this is a pseudo-random, pseudo-randomly convert to another 4-bit. And then there's nobody can guess the patterns. The only thing you can figure out how you're going to do this conversion, you just have to try all the possibilities. Okay, so this is basically the intuitive encryptions. Now, how many algorithms you have? There's many algorithms you can have. Okay, like Blowfish, DAS, IDEA, RC4, RC5. Those are pretty famous algorithms. And then there's Rindell, Serpent, Triple DAS, Twofish. All the algorithms, they can support 128 or 256-bit. In this RC4, they can even go to 2044 or 2048 bits. But normally, we consider 256 bits are good enough. But then, what I like is the AES, this algorithm, is it's not just secure; it's also very efficient. That's why I like these algorithms. Okay, now with this in mind, this is the first thing we call the symmetric encryptions, you can guarantee your message once being encrypted, then the hackers cannot guess what the key will be. They really have to use the fastest computer available to run that for a few hundred years, and then to get the keys. So we consider this is a secure, at least for now or future 10 years, at the very minimum, nobody can actually figure out what this encryption will be. So this is symmetric encryptions. Now, any questions so far?
So just curious on the ones, I think it was slide 7, you showed the different algorithms, and it had the one that had 2048 was, it said sometimes the keys are weak. I'm just curious with that many
This
bits.
one?
Yeah, the RC4. Why with so many digits, so many bits, how could you have a weak key with 2000 bits?
Right. So basically, that's two conditions. Okay, keep in mind the algorithms. Okay, the algorithm can do better or worse. So this RC4 is not a good algorithm. That's why you have RC5. So that's why there's some weakness. They have to compensate that with more bits. Okay, RC5 is better. So when you have a good algorithms, then you cannot guess. If you have bad algorithms, as I mentioned, right, this algorithm works. It's still encryptions. Our message +1 is encryption. And then when you do the decryption, it's -1. This is reversible, right? +1, your -1 is reversible. This is the algorithm, but this is very weak algorithm. You probably can, without computer, can guess what it is. So that's why you need to have a good algorithm. There's so many people propose the algorithm, and then the winner is really the AES. AES is a winner. Okay, so now if you look at the computer, you can see lots of algorithms use AES. Okay,
and you said, I'm sorry,
go ahead. This
I
one.
was just going to say, so you said the key is embedded when I send an encrypted email, the key is within that email, so that I send you an encrypted email, your computer can use that key to decrypt my email.
This is very good questions. Okay, that's why I would say anyone has a question, I seek the right questions. Now, you figure out our things. Okay, what I'm talking about here is called a symmetric key algorithms. Basically, when you do the encryptions, you have to have this key. When you do the decryptions, okay, you use, okay, I think I just accidentally captured. Your key is used for encryptions. Your key is also used for decryptions, right? So now the question is, how does the receiver know the key? I think that's why your question, right?
Yes.
How do I give you the key to you, right?
Yeah.
You send the key in the emails. There's no security at all. So at this point, I do not talk about how do you know the key, assuming you know the key.
Okay, got it.
Okay? Now, that's actually a very good question. How do you know the key I used for encryption? If you don't know how to do decryptions. Correct?
Right.
Okay, now, this is against intuitions. Intuitions, I use the same key for encryption, I use the key for decryptions. And then that happens for many, if you think about that, a few thousand years ago, people already know you can do that. Right? The original encryption decryption could be very simple, like a substitutions. You substitute A for B, and then in the end, you substitute B for back to A, you get encryption decryptions. So those kind of concept, okay, is the same key for encryption decryption. What really against intuitions is asymmetric encryption decryptions. This is something people don't realize until only recent years. This is something you think about. I encrypt with a key, then I decrypt with a different key. Can you imagine that? Okay, you encrypt with a key. Now, when you do decryption, you use a totally different key. Why this is so important? This actually can solve one of the 6 questions. How do you know? How do you solve the question? How to deliver the key to the receiving end? And this is actually the foundations for the e-commerce. Without these things, the internet, the e-commerce will not be able to in operations. Which I will explain that to you why. So now, this is more important concept than the previous symmetric encryption decryptions, because this is against people's intuitions. The only thing you have to remember now today, you do encryption decryption use different keys. Now I'll give you examples of why this works. Okay, so now encryption part. This first we have to get a concept called modulo. Modulo basically means the remainder. Okay, whenever you have a modulo, when you do these things, you got a remainder. 2 times 3 is 6. You multiply is 1. Because 6 divided by 5, your remainder is 1. So this is called a modulo. It's not division, it's called a remainder. So the remainder is 1. Now, with this operation in mind, I assuming my encryption key is 2. My encryption is 2. Assuming the message is M, this is my message. So now the cipher message or during encryptions, M times 2 mod 5. This is encryption, right? I said, okay, any operation you can do encryption, as long as you can find a decryption operations. Now the decryptions, you decrypt with keys 3, not 2. So what do? Your message, okay, the original message, right? The original message is M. Okay, so the when we do the decryptions, this is a cipher text is C times 3. Okay, equals C equals this things, right? So I just copy it over. It will be message times 2 times 3 times 3, right? So this still modified, but now you times 3. So original is times 2. Now you still keep this 2, but now I times 3. So what you get is this formula, correct? Okay, my M times 2 mod 5. Now it's M times 2. The message times 2 times 3 is my key, my times key. So 2 times 3 is 6. 6 mod 5, I said it's 1. Okay, now I got a message back. So what does that mean? I encrypt with a 2, and I decrypt with a 3. And I got a message back. So that's conclusions. The encryption key is different from the decryption key. This is just a math. It's very magic math. And there's just a 3 smart guy who found this one. It's called Asymmetric Encryption Decryption. Did I lose anyone?
I understand the concept. I don't understand how you, the question remains, how would you, on your, when I send my email to you, how does that work, that you have a different key? I mean, the math, I'm still trying to go through the math to figure out.
Okay, so first
how is it communicated?
Do you understand this math?
Yes.
Okay, do you understand this is 2 times 3 mod 5 is 1?
Yes.
1 times M is M. Okay, I got a message. Okay, is this a Diffie-Hellman? No, this is not Diffie-Hellman. Okay, this is not Diffie-Hellman. Okay, basically, you just keep this in mind. Okay, 2 times 3 mod 5 is 1. Right?
Yep.
So now you got this one. 2 times 3 mod 5 is 1.
Right.
1 times M is M. So it's back.
I mean, I understand that math, but I'm you know, when you have your, how can you use, how do the two, the sender and the receiver, how do they know what the encryption key will be. You still have your key. You have to communicate.
Yeah,
When you modify it.
Yeah, you're always ahead of me. Okay, so now
Sorry.
at this step, what I'm trying to say is you can encrypt with a message with one key, you can decrypt with another key.
Okay.
How do we use this one? I think that's your that's your question. How do we use this one?
Yep.
Right.
Yep.
Okay, let me see. How do we use the one? Okay, that's
Ryan, can I ask if this is a potential use case? Basically, in my experience, when I am given a key to encrypt any messages, right? And then another key, once whatever action item there is done, there is a third party that involves, right? Most of the time is IT. IT administers all these keys. They issue the one for encrypting, also the one for decrypting. So is it a possible use case to answer the question of, who manages the key to encrypt, and then, well, is there a third party that is involved in managing the keys, basically?
okay. We will get to that. Okay, so you guys are very eager to know the answers. Okay, let's just keep in mind we only talk two things. One is called symmetric encryption decryption. Another one talking about asymmetric encryption decryptions. We haven't talking about key management yet. Okay, so now that's the first step. Okay, now we can jump this one. Okay, so basically this is called the Rsa Encryption Decryptions. So basically what it says, okay, you have a message. If I can do this encryptions, I can do a decryption with a different D and get my message back. This is a little bit more mathematical proof. We can jump that. Okay. So now let's skip this proving part. Anybody interested in mathematical proving? We can do it offline. So I think the people are very eager to know what we try to do, how we can to apply this is asymmetric issues for the real problems. I think that's what people are really asking about. Then go this way. Okay. Let me see. Okay. So here, first thing. Now with this asymmetric, now you can see this first thing we can see now. Let me see. Do I have things that's working? Draw. Okay. Now. Okay. Okay, so now first thing, do I have okay. I have a pair of key for the asymmetric one, right? So I call them one's called key the private key. Another key I call public key. So this is a private key and public key. It doesn't matter which one is public, which one is private. Basically, use asymmetric encryption decryption. I have two keys. One is called private, and one called public. You pick one's public, the other one will be private. So I have two keys. Correct? I mean, I have a pair of keys, private and public. Now I have two guys, Alice and Bob. This is always used for the Alice and Bob. So when now I have define my two keys. One's called a public key. This public key, when I say public, means everyone knows. When I say private, nobody knows except yourself. So that's my definition. Now, how do you make a key public? You send it over over the internet because it's a public key. You can post it on the website. You can do whatever you want, because just make sure the other end knows this key. So it's assuming the assumption right now, the public is a non-knowledge. Everyone knows it. And then how to make it everyone knows it? Easy, right? You can call them, send to them with emails, text message. The purpose of public key is just everyone knows it called public key. Now the private key is really your private. Nobody should know. Okay, this assumption makes sense to you? Private, only you. You are the only person knows called the private key. Okay, everyone knows it's called public key. And when I have a pair of keys, I make this key one private, one public. Now, I can use this asymmetric way to do encryption decryptions. But why I don't use that? Okay, actually, I have examples here. This is an encryption decryption for the private for the asymmetric ways. You can see if you really want to use these things to do, they involve very big numbers here to do the modular. You get a message back. So keep in mind, asymmetric encryption decryption, it works, but it involves a lot of computation. And we may not want to use asymmetric way to encrypt a message because that takes too long. And in terms of efficiencies, this doesn't really have any advantage. So the way we do it is like this. If the Alice on the top is Bob, so Alice, first thing, they use Bob's public key. And then to encrypt with a session key. Session key means you can use that for communications and send that to Bob. Okay, how do Alice know Bob's public key? Because it's public key, everyone knows. And then the session key is used Alice to encrypt the message for Bob. So session keys, you cannot send this session key to Bob in the plain text. You have to encrypt that with Bob's private key and send it over to Bob. Now, who can decrypt this message? Bob. Why Bob can decrypt this message? Because this message had to be decrypted with Bob's private key. And who knows Bob's private key? Bob. Who else knows Bob's private key? Nobody. Who knows Bob's public key? Everyone. So that's why Alice can send a message. Send what message? Send the key for communication to Bob, use Bob's public key and send it over. When Alice sends this key over, now Alice and Bob will know this session key for communications. That's what answers the first question. How do they know the key? They cannot send that with email. They have to encrypt it. And then when you do the encryptions, you have to make sure only Bob can decrypt. Make sense? That solves the question about sending the key over securely. Nobody else will be able, even if this message is encrypted, they will not be able to know what it is.
So the session key is Bob's private key.
Yeah.
Okay. And a public key is, I mean, if it, yeah, I mean, what, why do you need a public key? You know, I mean, if everybody can see it, what good is a public key?
Okay, public keys everyone knows. Okay, but your question is, does Bob have a public key? Okay, this assumption is Bob has a public key.
Right.
Okay, so now later on we will tell you why the Bob has a public key.
Okay.
At this moment, we says Bob has a public key.
Okay.
Okay.
Sorry, I don't mean to keep getting it.
Yeah. Okay. So I know you're just one step ahead of me.
Okay.
So just now we just say Bob has a public key. So if Bob has a public key, this works, right?
Okay. Yep.
Okay, that's good. So that's what all we want to know. Bob has a public key and this thing works. Right? So then you can set up channel connections. Okay, now this is good enough. Okay. Let's move to, okay, we will come back to here, why the Bob has a public key. But then at this moment, we move to second things, authentications. I said we have three things for the communication, right? So remember that? authentications, confidentialities, integrities. So what about authentications? Authentication is basically to identify identity of the party involved. That's authentications. How do you do the authentications? Authentication has to be done through a trusted third party. So what does that mean? Trusted third party. Okay, me and a SIG. Okay, now we are talking. At this moment, okay, assuming we're talking to the internet, and then I don't know SIG, and then SIG, okay, I'm SIG. Do I believe that? No, I don't. So I have to have a third party that tell me, okay, this is SIG, and I know him very well, and I trust this guy. So this is trust third party. And then I will believe, okay, yeah, I now I know who he is. So this is kind of centralized. You have a central authority tells me who they are. So this is one way. Second way, just in case there's no central authority, that's why everyone goes to a distributed way. Then we need to have a pre-shared secret between the two parties. Makes sense, right? So you will have think about you're going to meet someone in San Francisco. You've never seen this one before. Then how do you know you're going to find the right person? So before you go for the date, then you say, okay, this person, we're going to read San Francisco Chronicle 1 week ago's newspaper. Maybe you're going to read that upside down. So this is just secret. And then you find someone to do that, you know that's probably the person you're looking for, because you are only those two persons share the secret. This is called pre-shared, means before you go there, you already know what kind of secret. Okay, nobody else knows the secret. Only the two party knows. If you find that secret, then you know who they are, right? So that's only two ways possible. There's no third way. Okay, so now, so this is intuitive, right? You see, okay, there's either you have centralized way or you have pre-shared secret. The pre-shared secret means you know the secret before you even engage in the conversations. So that's only two possible ways. Okay, now let me give you a quiz. Okay, if you log into your account, use your username and password. Okay, now which way you are using? Because the server side has to identify who you are. So this is called the authentications. Otherwise, you have a bank account, everyone log into that. That's not good. They have to authenticate the person is a legitimate person. So use a username and password. Which way we are using right now? Use a password. Use pre-shared, right? So the password is being established when you set up the account. So you pre-share secret this password. Only you know the password. Only the server knows the password. Then when you log into the server, when you use the pre-share secret, then they can authenticate you to a password. Correct?
Yes.
Okay, so this is a pre-share secret. What about the trusted third party? So the trusted third party is called the VeriSign. Okay, the VeriSign will confirm the identity of the party. Then it's also fine, right? You have an authorized person. We trusted the VeriSign. So this use a trusted third party. How does the VeriSign works? Okay, now this is how the VeriSign works. This is a guy, Alice. This is Bob. Okay, now Alice says, I'm Alice. Bob will believe that? Probably not. Okay, so now Bob sent a message R. The message R. And then the Alice will decrypt, okay, that message with Alice. Okay, send this message to Bob. And then Bob will say, send me your public key. Send me your public key, because public can be sent anywhere you want to send. Okay, you send this a public key. Now, then the Alice will send a message. Okay, so now basically, the Bob will compute. Okay, now with this public key, Alice's public key, do the encryptions. Okay, so I think the same thing here. Okay, so what do you try to do? Encryption and decryption. Okay, put it this way. So basically, Alice encrypt with his private key. Bob decrypt that message with his public key and get this message R back. So what does that mean? So the whole thing here, what we try to say is Bob want to make sure Alice knows his private key. Okay, who knows Alice's private key? Only Alice. So how do Bob know this is Alice? If Alice, you can demonstrate me, you know Alice's private key, then I know you are Alice. Okay, let me say one more time. I think I probably lost someone. Okay, here's Alice and Bob. Now, what we try to do, if Bob want to believe this Alice, so this Alice has to show to Bob, she knows the Alice private key. Correct? If you know Alice private key, Bob will believe this is Alice. Same way around. Okay, if Bob knows his private key, then Alice will believe this is Bob. Okay, the assumption right now, everyone has public private key. So why we have Alice public private key, I will go to that. Okay, so now, so what do you assumptions? If, okay, everyone has a public key and private key, Alice has her own private key and public key. If you can demonstrate you know your private key, then Bob will believe her. Now, how do you believe? How do you to show you have Alice? You have Alice private key. What Bob did, they use Alice's public key to encrypt the message, and then ask Alice to decrypt that. If you can decrypt the message, will only be decrypted by Alice's private key. That just demonstrate you know the key. Does it make sense? If you know the private, if you know Alice's private key, you are Alice. Otherwise, you are not.
So do Bob and Alice establish a connection to where Bob can get access to her public key? Like you send an unencrypted email and you can pass the public key that way?
Yeah, so basically,
okay.
I encrypt it with Alice's public key and send a message to you and say, okay, now, if you're Alice, decrypt this thing. If you can do that, you are Alice.
Okay.
If you're not Alice, you cannot decrypt it.
So the public and private are basically asymmetric keys.
A public key is everyone knows, okay? So basically, Bob knows Alice's public key. So use Alice's public key, include message, send it to Alice to say, show me your Alice, decrypt this one.
Would you say that the public and private key are asymmetrical?
No. When you say public private is asymmetric, yeah, asymmetric,
okay.
different. They're different.
Okay.
Yeah. Okay, so this is called authentications, right? Without pre-shared secret. Otherwise, you have the pre-shared secret. Here, we do not pre-share any secret. Basically, I just request you have a public and private key. Then I can you can demonstrate or you can show your identity by demonstrate you know the private key of this Alice. Okay. I think pretty silent. Following me or not following me?
I have a couple of questions. For a specific public key, how many of do we have private key are duplicate the separated? Let me see. One public key have only one private key pair, or
Yeah.
it can be many.
No, it's always a pair. It's always a pair. Okay, one public key, one private key. There's always a key pair. Then you pick one as a private, and then the other one will become private. So you just keep it one as a private. The other one will be public. This is called a key pair. There's always a key pair.
Another thing you mentioned about the session. Typically, how long that a session was defined, and do they have some time limits?
Say one time, the second?
Session. You define there's a session. You send in the session key, not really your private key. And in the session key, how long that a
session key? Session key. You mean the key sessions?
Yeah. That a session. How long that a session typically make sure you're not passed.
Oh, this is a protocol. Okay, we don't talk about that. Okay, this is a protocol issues. But right now, once you have session key, you can communicate. That's all. Okay. But once you go to session key, that's a different story. Okay. Let's don't get into that. Okay.
When you ask, for example, Bob said try to authenticate Alice, and how long give them a time to authenticate herself? You send the information to to Alex. Alice try to verify him herself. How long you have to? There's a time limit, so you try to finish the verification, isn't it?
No, it's just back and forth. This happens within seconds, within 1 second. Just ask this one, give it to me, what's going to give to me. So that happens very quickly, microseconds, milliseconds.
Yes, but do they have like a protocol defined that the time frame? You have to answer this question in certain time frame. Otherwise, you might be.
No, again, you're talking about protocols, okay? So we are talking about the principles. That's a different story.
Okay.
Okay, so let's don't get to that part. Okay, just understand how we do the authentications. Okay, once you define protocols, then you have to define those security issues. So that's why you have this session time. So don't worry about that for the time being. So now what I'm trying to say, okay, with this private key and public key scheme, you can do authentications, right? So now, how this is a CA VeriSign do this authentications, right? I said, okay, CA is a trusted third party, right? And in here, there's no CA here. There's no CA. So why the CA, the CA VeriSign become a trusted third party do all authentications? The CA business just authenticate. It's like the trusted third party. They authenticate everyone, and then the trust get money. So that's back to the sixth question: how the CA make money? They sell you keys. Okay, everyone can apply for public-private keys. Then they said, okay, I don't have that. Okay, you don't have that, but then business has it. All the business, even do the internet business, they have to apply for the public-private keys. So that's where the money comes from. And for the individuals, you may not have the private-public keys because you don't pay for it. And when you pay for it, that's the money, VeriSign's revenue. So if you don't have the public-private key, then what are you going to do? You use a pre-shared key. So you establish your username and password. It's pre-shared keys. But now, how do you, the business, whenever you go to a business, you like in a bank, bank has a website. So the website they use HTTPS. Then they have to get we call the certificate is basically the public keys. So the bank has to go to CA website and buy their authentications, the public and private keys. That's why you go to any website to do business, you check, do they use HTTPS? When you use HTTPS, basically they use CA to do the authentications. Now, let me see, do I have that a little bit here? Okay, so here's how it works. Okay, basically that's how it works. Here's the HTTPS. Here's the server side. Here's your server side. So the first thing you request, okay, I want to come to here, and then the server side send its public key with the certificate to the user. Basically, user is a browser. Where the certificate comes from, CA give the certificate. So CA sells the certificate to the business. So that's what their revenue. Now the browser or the user ensure that certificate is unexpired or is really legitimate. So how do you do the legitimate? I think I missed one thing. Let me go back to one thing. Okay, here is one thing called a digital signature. This is also important. So the digital signature is for the like the normal signature is just to verify the generality of the piece of work, right? So this digital work. So in this case, right, how do you know if I send a message to you? How do you know this is a message it should be generated by me, not by someone else? So that's how it works. Okay, so here's Alice as a Bob. We use Alice and Bob. So in this Alice's computer, they have a private key is Alice. Whenever you have private key means your identities. Okay, now what do you do? This is a public key. This is the Bob's private key. This is Alice's private public key. So now if you send a message, what a digital signature means. So what is supposed to, this is my plain text, and I encrypt that, okay, with my private key. I encrypt that with my private key. Now I also encrypt that with my public, use Bob's public key. When I have done this thing, I send it over. So in the Bob, so the first, they have to decrypt that with his own private key. Okay, the second thing is what they do. They have to decrypt that with Alice's public key, and they get a text back. So now, what is a digital signature? Digital signature is the encryption with your private key. Why this is a signature? Okay, signature means only yourself can sign, nobody else can sign. Now, who knows your private key? Only yourself. So if you encrypt this message with your private key, that means this is your signature. How do people know this is your signature? If they can decrypt that with your public key. Public is known to everyone, and they get this message, they can 100% sure this is being signed by Alice. So that's why I call it the digital signature. Okay, this is very important. Okay, like you send a piece of message to me, you go through the internet. Now, how do I know this message is sent by you? Then, in this case, assuming you have public key, private key, all you do, you just have to sign with your private key. then I will know this message is 100% sent by you. Because only you have your own private key. So this is called digital signature, basically. This is called digital signature.
So in,
Okay, now,
I was just going to ask you, your transmission line there, you have the EBDAP in your transmission line. Is that what's the EB there? That's
okay.
Bob's public key. It's just a combination of Bob's public key, Alice's private key, and the P is the message you said.
Yeah, P is a message.
Okay.
D is like okay, there's like attached to it. Okay, so forget about that because this is just a notation because there's a long text like copies just a part of it. So just keep in my word. Okay, you have a piece of message. Now you want to sign that, you just use your private key to encrypt it.
Okay.
Okay.
Right.
To prove this is your signature because you use your private key to encrypt. Nobody else knows your private key, so that can guarantee is your signature, not anyone else's signature.
Right.
Right? Make sense?
Yes.
Okay. Now back to here. When a CA in this case, when the this is a server like a bank. Okay, bank will send the user what they send. They send their public keys. So now the question is, how do I know this public key is indeed this bank's website? The bank website's public key, right? So if you're a hacker, you can fake because the public key is known to everyone. You can just this Chase Bank's public key, so you send to the user. Okay, this is my public key. And how do I know this is your public key? Okay, here's where the CA comes to play in the role. The CA will sign this key with his own digital signature. And then the user can verify the signature by decrypt this public key, this certificate with CA's public key. CA's public key is known to everyone to verify this indeed a public key of the Chase. Okay, so that's where the CA comes in. CA has to use his own digital signature to verify this is the public key of this guy. With that, then you can trust, okay, this is Chase Bank. So you can do the communication with this guy. So this is called authentications. Now, how do the bank know this is the user? The user does not have public key and private key. So the user and the bank authenticate user by username and password. This is called a pre-shared key. Because the individuals, nobody no business can force the individual to buy the certificate. But business has to buy the certificate. Okay, this is business has to pay for it. So that's the business. So now you can see as the CAs in here to digital sign this certificate. So technically, the identity of the business is being verified through a trusted third party. This is the VeriSign. So VeriSign digital sign the certificate just to assure any individual consumer, okay, that what they receive the certificate from the business is indeed that business. So then you can do business with them. So that's what the HTTP is about. HTTPS is the protocol. So with this HTTPS, you can 100% sure you are talking to a website which is genuine. Okay, look like no questions. Okay, let's move on. Okay, now, so they has other securities. For example, you nowadays people, you know, the individuals, they don't have public key and private key. They use a mobile code securities. So the questions, what is a mobile code security? Is a pre-shared third party or what it is?
I would think pre-shared.
Why is pre-shared?
Because, well, I'm trying to think of who the third party would be, and I'm not coming up with anybody, so I'm thinking pre-shared.
Yeah, so your phone numbers, whenever you register for the bank account, you give these numbers to the bank. So that's before you next time to engage any communications, they verify the pre-shared secret with the phone number. And then you just verify, oh, you have this code. So this is pre-shared,
Okay.
right? There's no trusted third party in between.
Okay.
Okay, make sense? Okay,
Yes.
now move this this part. Okay, now we explain those things about your question, why you don't have a public key, private keys. Now, who has a public private keys? Business has a public private keys. You don't, because you don't pay for it. But then you can use a pre-shared with the business, so they still can authenticate you. But the business has to buy the certificate, use the CA to authenticate them. Otherwise, you will not be able to trust their business. Right? Okay, now, here's the thing. Authentications. So we said, okay, authentication can be done either centralized way, trusted third parties centralized way, right? Or pre-shared. Can we do a third way? So I said, okay, no, you cannot, right? But now, think hard. Can we really do it? Well, I think you still can do it, right? But then not necessarily 100%. What does that mean? When I say the centralized way, because your authority, you trust the authority 100%. Is that way you can trust your friend, but your friend is not a really centralized authority. This is called distributed way. Okay, now assuming, okay, Charles, I can trust Charles. So okay, Charles tell me this is sick. Okay, this is sick. But then maybe there's a third, another people who doesn't really know Charles, and doesn't trust Charles. So now this is the thing. In a distributed authentication, it's not a centralized authorities. It's good enough. It's called a trust of ring of trust. If there's I have enough people tell me this is sick, I think that's probably sick. I mean, don't need a centralized authority. I just need a distributed, a bunch of people tell me this is the guy, and I believe it. Is that 100%? Well, because I don't really have a centralized authority, it's not 100%, but it's good enough. So that's how we can get authentication without a centralized authority. So that's basically the blockchain. Blockchain is talking about decentralized. Okay, if you don't know blockchain, but actually you heard about what blockchain is about, right? blockchain is about decentralizations. And how do you do decentralize? Without a centralized authority, you will count on every single people in the community as a way of doing authentications. Correct? You have a community, everyone knows each other. And then you do not need another central government to say this is A, this is B. Because your friends will tell you this is A, this is B, and then you believe them. That's good enough. So this is called distribute authentications. So the idea I want to talk about today is three things. Okay, I didn't really talk about integrities. Integrities, I said three things you have to keep in mind, right? First one, confidentialities, confidentialities, authentication, integrities. Now, how do we do the integrities? Integrity basically use digital signature. Because you sign it, people cannot change it. You have a digital signature. That's keep it integrities. But our focus today is really try to get to blockchain. So the blockchain has been seen as important technology which can solve the authentications problem without the centralized management. So that's what the blockchain is about. So how are you going to do that? So the ways is called distributed authentications. So the distributed authentication means I don't need pre-shared secret. I don't need to centralize the authorities. I just count on every members in the community and I trust them. So this is basically the blockchain is about. This is decentralized authentications. I hope at this point, you know what I talk. I mean, next week, we're going to talk about blockchains. So we have to go through these fundamentals. So you see why this blockchain works and what really blockchains try to against. They try to against centralized authentications. Okay. Now, what's the problem with centralized authorities? Why people against it?
Control. People want control of their own identity.
Okay.
Without relying on Google or Apple or Microsoft.
Yeah, basically centralized has a big advantage, is convenient. Okay, it's very convenient. If you have a centralized things, do all the things will be easier because you just go to the centralized authority, who this guy is and what do they want to do. A lot of things can be solved easily, but then this is also a big problem. First, you have to trust them 100%. And then I think that in this trend, people don't want to trust anyone 100%. That's one thing. Second thing is really the efficiencies. Another thing is reliabilities. What about this centralized authority really failed? So those kind of things people think about, oh, we want to distribute away. It's a democratic way. Okay, basically, I don't trust any single person as my centralized authority. I just trust the majority of people, what they tell me. So that's basically about the blockchain. Okay, and that's against like the bank or centralized bank is kind of centralized the point authorities. They issue you if you do any transactions, go to a bank, goes through a bank, right? It goes through a bank, then you can trust the bank. If a bank is trustworthy, then you do all the business and go through the bank, right? Because bank has this authority and also has this trust that it goes through this bank. But now if we really go to the blockchain, it's just against the normal way of practice. I don't want a centralized authority. I just want to do things in a distributed way. So we don't really say like a democracy, which is distribute is computer word. Okay, distributed way means there's no centralized. Centralized, you have a centralized server, your server is down, everything's done. Everyone has to go to centralized server. It create a bottleneck. You might have efficiency issues, and another things you don't like. You have to pay a fee for that. Okay, so that's basically what I try to do today. And then I hope my explanation is clear to everyone. If you have questions, we can discuss further. But then I should lay a foundation about my next seminar on the blockchain.
So, so slide 27 was that just another?
Which slides?
Slide 27, was that? Let's see.
Oh, this one?
Yeah.
Oh. No, this one just talking about secure emails.
Okay.
It's a secure emails. It's the same thing, but I think it's not so important.
Okay.
Okay, you can secure emails.
Sure. And then is so I guess we'll get into it, but it's so self-sovereign identity, is that the self-sovereign identity utilize blockchain, or that might be next? Self-sovereign identity, SSI, it's like another way of verifying your identity.
Self, oh, that's different issues. That's different issues.
Okay, it's not necessarily blockchain related.
No, blockchain.
Okay.
Blockchain basically, if you think about it, blockchain just distributed way of doing authentications. That's all.
Oh, okay.
Yeah. So, I go through 1.5 hours just explain to you about what is the confidentiality, what's the authentication, what's integrity. But actually, the bottom line is one thing, right? The bottom line is one thing: is how you can make confidentiality just encryption decryptions. Now, with this the asymmetric encryption decryption, it solves big problems of authentications. But then with this, the solution for this authentication actually is a centralized solutions. But now I get to the blockchain. They use both. They use all the centralized they use asymmetric encryption decryptions. But then the bottom line is, they use a signature, right? So they still use signature. But then the bottom line is now we try to get rid of the centralized authentications. I still can do authentications. The decentralized movement, basically. Okay. Is this the concept clear? Because we didn't really go to the implementations. I only just trying to explain this concept, because we're going to use this concept in next time.
Yes, thank you very much.
Okay. Sig, you are clear now?
Yes.
Okay.
Thank you.
Okay, that's good. And what about any other questions? Okay, for now, you have any questions? Okay, I think there's some questions being asked here.
Can I ask some implementation question?
Oh yeah, go ahead. Now we can answer any question you want.
Essentially, we have the encryption, decryption, also the blockchain, whatever. How do we solve this kind of speed issues? So essentially, where we implemented this encryption, like in the computer communication, should we implement in the hardware, in the switch or router to information out, or has to implement in the software and taking the CPU power?
Okay, so for the implementation wise, there's a chip implementation, all the libraries. Okay, libraries is software. So it depends on what you do. For the high-end routers, they have the chip encryption decryption just for speed concern. For the computers, normally they just use the libraries.
Okay.
Yeah. So if you do any home routers, they use libraries. You use those big routers, especially for the high end, they all use chip solutions.
Yeah, in the cloud computing, this kind of thing become very critical for all the information transmission or encoded and also encrypted. So
Yeah, I think depends on your requirement. On the general computers, laptop, desktop, I never see any hardware implementation. All uses libraries. This is the algorithm itself is a standard. Okay, all being implemented in the libraries. You don't have to do it yourself. And then for the performance, then you just buy a chip, and chip can do it. Okay, if there's no questions, that's all for today.